Hi everybody, this is the lecture for section 5.6, center of mass. So this is a important calculation using multiple integrals, double integrals and triple integrals. Consider a region R in the 2D plane. So we'll do the explanation for 2 dimensions, and then for 3 dimensions it's more or less the same. Consider a region R in the xy plane and a function fxy on R, which represents the density of R in units of mass per unit of area. So you've got some kind of flat thing and flat-ish thing, and it's got some kind of variable density. It's not a uniform density throughout. So you can think of it as a two-dimensional object, or maybe it's kind of got a two-dimensional facet to it, and then there's various thicknesses of it on either side, which kind of gives it a measurement of units mass per unit area if it's got some kind of variable thickness in the third dimension. So I mean various ways that could come about. Okay, as we discussed before, so it was in section 5.4. For a 3-variable function, when you have this density function f on a region R, then the total mass is just the multiple integral for however many dimensions you've got of that density function. Right, so you have a density function in 2 dimensions, unit mass per unit area. Or you have a density function in 3 dimensions in unit mass, not per unit area, but for unit volume. Unit mass per unit volume. Or in 1-dimensional unit mass per unit length. So if you had like some sort of rod, the variable density. So as we discussed before, so we did it as a 3-dimensional example, but it's the same with 2. The total mass is just the double integral of the double variable function, the 2-variable function, or it would have been the triple integral of the 3-variable function. So given this, we would now like to know what the center of mass is of R is. So you've got this region R, and it's got some center of mass x bar, y bar, right? And what the center of mass is that's kind of the balancing point of R. So I mean, if R is flat and you put it on a 1-point fulcrum on the head of a nail or something like that, if you were to put it on a head and a nail, I mean, theoretically, there's some spot on which it'll balance, and that's the center of mass, right? Or if it was a flat object, and you kind of want to chuck it like a frisbee, then it's going to spin around its center of mass, right? So the balancing point, center of mass, center of rotation, or whatever, however you might like to think of it. Now, by the way, it's not that the density function has to be variable. It could be a constant density throughout, nice uniform density. But if the shape of this thing is a little sort of weird, is a little irregular, and you wouldn't know what the center of mass might be, you can calculate it doing this calculation I'm about to show you. So if you remember Archimedes' lever law, so Archimedes' lever law says, given point masses M1, M2, all the way up to Mk, along a rod of negligible mass, the center of mass, at coordinates x1, x2, up to xk. So that long rod, thin rod of negligible mass, it's got it's got coordinates. It's coordinatized. So each mass is at an x coordinate, right? So something like this. All right, so this is x1, x2, x3, x4, x5, and here you got mass 1, mass 2, mass 3, mass 4, mass 5. Okay, in this case, the center of mass, right, x bar, so that's the balancing point on the rod, is equal to the total moments so x bar equal to the center of mass is equal to the total moments divided by the total mass. So this is m1 x1 plus m2 x2 plus mk xk over the total mass, m1, m2, mk. So moments are mass times coordinate. Mass times coordinate plus mass times coordinate plus all the way up to mass k times coordinate k divided by the sum of the masses. Total moments over total mass. Okay, so Archimedes' lever law. To apply Archimedes' principle, to our situation for R, okay, what we do is we subdivide R into subrectangles, like we've done before. R into subrectangles of area delta A equal to delta X, delta Y. Right, so you subdivide horizontally and vertically. And then within each region, within each subrectangle, pick a sample point. near the center, say, of the rectangle. Choose a sample point x, I, y, j. So in this rectangle here, you've got your sampling point, say right at the center, x, I, y, j. All right? As long as your density function is continuous, which, I mean, it would be. You wouldn't have some funny jump in density at some point, or some density approaching infinity. I mean, under most normal circumstances. So assuming that the density function f(x,y) is continuous, then it is relatively constant on each rectangle when delta x and delta y are tiny, right? Which is the situation that we're looking at, because we're going to let delta x and delta y both go to 0. So as long as this is really tiny, f doesn't vary very much on that little rectangle. Okay? Thus, the mass of the rectangle is approximately, right, f, x, I, y, j. The density at the sample point, right, units mass over units area. So fxy is in unit mass over unit area, times delta A, which is units area. Right? You cross those out and you get mass. Units of mass. So the mass of the tiny rectangle is approximately the density at that point. I mean, it does vary, the density around here. But since it's really tiny, it doesn't vary that much. It doesn't vary that much. So as long as you're relatively constant here, you just take the density at one point as an approximation for the density of the whole thing. So when you have a constant density, right, when you have a constant density, then the mass is just constant density times area. Units mass per units area times area. Give you units mass. So the mass, total mass, oh, I'm sorry, I'm explaining mass. I'm not supposed to be explaining mass. As long as the density function is continuous, it is relatively constant on each rectangle when delta x and delta y are tiny. Thus, the mass of the rectangle is approximately this. So the moment of the little rectangle in the x direction only. So we're talking about the moment, which is mass times coordinate, in just the x direction only, is approximately, right, mass times coordinate, x coordinate, which is equal to x, I, f, x, I, y, j, delta A. Is just the x coordinate times the mass, and the x coordinate is just xi. So we're just taking the moments just in the x direction on the x-axis. Forgetting about the y direction for a moment, we'll do that separately. Archimedes' lever law is just for stuff along an x-axis. Total moments over total mass. So we're just finding total x moments over total mass. And then we'll do total y moments over total mass. So total x moments over total mass will give us the x bar. So that's not the point at which it balances, but the x coordinate on which along which it balances on an edge. And then we'll get the y bar, and then we'll get the balancing point for the whole thing, center of mass for the whole thing. So we're doing the x center of mass, and then the y center of mass, and then the complete center of mass is just, the pair of points. All right, therefore, x bar is approximately, right, total moments, is equal to total moments over total mass, which is approximately equal to the double sum over I and j, xi, f, xi, y, j, delta A, over total mass. And then the mass, like we were saying before, is approximately f, xi, y, j, delta A. The approximation gets better as delta y and delta x both go to 0. Better and better as delta x and delta y both go to 0. Therefore, x bar, just the center of mass in the x direction, is equal to the limit as m and n go to infinity of this fraction here. Of this. Right, but the limit of a fraction is just a fraction of the limits, right? So this is a limit as m and n go to infinity. Limit as m and n go to infinity of these things here, but these things are just the standard form for a double integral. Which is equal to, so this is the double integral over r x f x y d a. Let me put the x bar here and here. And this is just the double integral over r f x y dA. But like we were saying, this is just the total mass. So this is equal to double integral over r x f x y dA over mass of r. Right, so x bar is equal to 1 over the mass of r, right, which is equal to this, double integral x f x y dA. Similarly, y bar is equal to 1 over the mass of r. So let me put these on the same page. That's fine. Yeah. the double integral, it's the same calculation, y f x y dA. And notice, right, all of this where mass of r is the double integral over r f x y dA. So density, this is density, that's area. So density times area is mass, and this is x coordinate. Right, so this is total x moments. Mass times x coordinate, right? Total x moments, the double sum over x fxy delta A. So that's total x moments over total mass. This is total y moments over total mass. So it's pretty simple. It used to be, I don't think we do it anymore. I haven't taught, no, I did teach Calc 2 last summer. Since we adapted the new book, we used to teach these center of mass calculations in Calc 2, but that was just using single variable functions, and it was definitely more of a limited sort of, had limited applicability. It was only for constant densities, and it was for, you know, the x coordinate, the x bar was this, but the y bar was some really awful sort of formula. Okay, so here, I mean, they're really easy. They're really easy to remember. Not equals, this is times. They're really easy to remember. They're just 1 over the mass, y fxy. Double integral y fxy. 1 over the mass, double integral x fxy. Where mass is just the double integral of f. In 3D, it's the same thing. In 3 dimensions, for a 3D region R with density function f, x, y, z in units mass over units, not area, but volume. Right, the mass of R is just the triple integral over R of f, x, y, z, dv. Like we were talking before, I mean, you really, to me, the most natural way to think about a triple integral is that the function represents the density of R at a given point. And that therefore the triple integral measures the total mass of R, where you have density in units mass per units volume, and then this is units volume. So you triple sum that up. So that's the most natural interpretation, because it doesn't have an interpretation as a, you know, as a volume of something that, you know, you can sort of visualize easily anyway. So the mass is that, and then x bar is 1 over the mass of R, triple integral over R, x, f, x, y, z, dv. All right, it's the same sort of setup and calculation as before. So x bar, y bar, z bar. So the same kinds of formulas. It's got a nice uniform description, and there's no weird, you know, the formulas for x bar, y bar, and z bar are all the same, are all analogous, and it doesn't have one being something simple and the other being something strange. Okay, so let's take an example. And I'm going to do one with a constant density function, because even in the case of a constant density function, it beats the single variable description. That used to be in Calc 2, but probably wasn't when you took it. So, for example, the region R shown has constant density fxy equal to 1, 2D region. Okay, so I'm just going to make a polar rectangle. So let's say that this is the circle of radius 2. This is the half circle of radius 1. And, you know, that's our region right there. And it's got a constant density. So we're going to guess that x bar, y bar is where? Well, I mean, this thing is nice and symmetric around the y-axis. I certainly haven't drawn it that way, have I? A little better. There we go. It is nice and symmetrical on the y-axis. So the x bar is definitely 0. Okay, x bar is for sure going to be 0. Y bar, I don't know. I mean, is it going to be here? Is it going to be bigger than 1, less than 1? I'm not sure. I don't have too much of a feel for it. Intuitively, it turns out that it's actually a little bit less than 1. So we're going to, you know, that's for sure. The x bar is 0 from an intuitive standpoint. That's absolutely clear. But y bar, whether it's bigger than 1 or less than 1, we'll see. I mean, I did the calculation already. It'll be kind of close to 1 for sure, but it actually winds up being less than 1. All right, so the mass of this thing, so find the mass and center of mass. For r. Oh, and by the way, r is 1 less than or equal to little r, less than or equal to 2. We'll do it in polar coordinates. 0 less than or equal to theta, less than or equal to pi. Right? To describe r in polar coordinates. It's a polar rectangle. Right, so the mass is the double integral over r of 1 dA. So that's the double integral from 1 to 2. 0 to pi, r dr d theta. So this is integral from 0 to pi, antiderivative 1/2 r squared, from r equals 1 to r equals 2, d theta. So this is equal to, so what do we have here? 2, this is 4, so that's 1. So 1 minus 1/2. That's just 1/2 d theta. So the whole thing is pi over 2. Right? At 2, you get, and at 1, you get a half. Oh, no, 2 minus 3 halves. So that's 3 pi over 2. So that's the area. 3 pi over 2 units squared. All right, x bar is therefore going to be equal to the double integral over r of x dA. Right, x times fx. But f was just 1, had that constant density. So this is the double integral from 1 to 2. 0 to pi. So x is r cosine theta, and then dA is r dr d theta. So integral from 0 to pi, from 1 to 2, r squared cosine theta dr d theta. So antiderivative with regard to r, 1/3 r to the third cosine theta d theta. So r equals 1 to r equals 2. So integral from 0 to pi, so this is 8/3 minus 1/3, so that's 7/3 cosine theta d theta. But this is equal to 0, right? Because we're integrating cosine theta from 0 to pi. Right, so here's at 0, pi over 2, and then at pi, right, cosine theta looks like this. Right, so that integral is 0. So x bar is 0, as it should be, right, like we were saying. Right, so that confirms our intuition. And then y bar is equal to double integral over r y f x y dA. So double integral over r of just y dA. So that's the integral from 1 to 2, 0 to pi. Y is r sine of theta, r dr d theta, which is the integral from 0 to pi, integral from 1 to 2, r squared sine theta dr d theta. We already calculated this integral of r squared from 1 to 2, right? It's 1/3 r to the third from 1 to 2. So that's 8/3 minus 1/3, 7/3. So 7/3. Oh, I'm sorry. I forgot to put 1 over the mass. That's fine. So I forgot to put 1 over the mass for all of these things. 1 over the mass. The mass was what? 2 over 3 pi. Two over 3 pi. 2 over 3 pi. Right, the mass is 3 pi over 2, but we're doing the reciprocal. But that's 0. So here, 2 over 3 pi. 2 over 3 pi, 2 over 3 pi. So that was 7/3 sine theta d theta, 2 over 3 pi. So this is equal to 14 over 9 pi antiderivative sine minus cosine from 0 to pi. So this is 14 over 9 pi. So negative cosine of pi is 1 minus plus cosine of this, that's 2. So that's 28 over 9 pi, which is approximately what? So 28 divided by 9 times 3.14159 equals 0.990, so it's just a little bit less than 1. 0.990 to 990. 0.990, so slightly less than 1, which confirms our intuition. Right, so that's a real nice example. I like these center of mass calculations a lot because, we kind of know what well, not always, but in lots of situations, we kind of know what the answer is going to be ahead of time. Right? So we do the integration, we do the calculations, and then we see our intuition borne out, right? I mean, again, the x bar, y bar, whether it was bigger than 1 or less than 1 wasn't clear, but it seemed like it was close to 1. Okay? And as a matter of fact, it is. By the way, this is a nice example of something. If you've ever seen, so I mean, you've got this curved shape, right? If you ever been to to the circus or whatnot, and you ever seen someone on these really high tightrope walks, right? Like they string a tightrope, across Niagara Falls or something like that, and some guy will, or gal will walk across this tightrope, and he's got this balancing pole. And the balancing pole is curved, or, the balancing pole is so long and flexible that it does curve as he's walking. So when that balancing pole curves like that, the whole center of mass of him and his pole, it falls below the wire. Right, so some guy's walking on the wire, so here's the wire going out to the distance, right, and the person is on the wire. And he's holding his balancing pole, and that balancing pole is flexing down like that. The center of mass goes down below the pole. So you can do this with a one-dimensional, a very thin, thinner than this region. So instead of from 1 to 2, you do like 2.9 to 2 or something. And then you'll see definitely that center of mass is down below the level of the wire, as long as the curve is enough. So it certainly makes the act of balancing here a lot easier, as it should be, because this person doesn't want to fall if he sneezes or something. So that's a cool example for that reason as well. Okay, so that's the lecture for this section.